Hello viewers, today we are going to discuss general procedure of analysis of flange section. Now as we have already covered two short videos on the topic of flange section analysis, therefore I am going to take a little liberty and I have already solved this numerical example on analysis of flange section. We will run through the steps. So I urge you to keep your focus on my cursor. So we have to analyze a flange section which has width of flange BF equal to 700 mm, depth of flange DF equal to 90 mm, effective depth of 650 mm, width of wave, that is width of this beam, equal to 230 mm, and it is reinforced with 5 bars of 25 mm diameter on tension side. Let us say the grade of concrete is M20 and grade of steel is Fe415. We need to find out moment of resistance of this cross section. The first step that we do is we assume that the section is under reinforced. If the section is under reinforced, at failure, steel on tension side is going to have the stress of 0.87 Fy. Therefore, Tu will be equal to 0.87 into Fy into pi by 4 into 25 square into 5, which is area of 5 bars of 25 mm phi. Therefore, it is 0.87 Fy into AST. This Tu turns out to be 886150 Newton. Keep track of units. As we have substituted 415 in MPa, that is Newton per mm square, you will get Tu in terms of Newton. The next step that we do is we assume that the neutral axis is at distance df from extreme compression fiber, that is xu is equal to df. If we make that assumption, then corresponding stress block, stress distribution diagram will be seen like this. The entire stress block therefore would lie within the flange, and therefore it will correspond to the uniform width of BF, that is 700 mm. So in that case, Cu will be equal to 0.36 into FCK, that is 20, multiplied by uniform width BF, that is 700, multiplied by XU, but XU is assumed to be at DF, therefore it is 90. If we work out that, Cu turns out to be 453600 Newton. This value is less than the value of Tu. For equilibrium, we want Tu equal to Cu. Therefore, in order to have Cu greater than this value, which is equal to Tu, we must have neutral axis within the wave. And therefore, the conclusion from this is Xu is greater than Df. Had this value been greater than Tu, then that means we require less neutral axis at lesser value than df. In that case, our conclusion would have been xu is less than df. But in this case, as the value of cu is less than the value of tu, you would require neutral axis to be at lower level so that the area on compression side increases. Therefore, xu must be greater than df. The next assumption that we do is 3 by 7 xu is equal to df. So what is so specific about 3 by 7 xu? So up to 3 by 7 xu from extreme compression fiber, we know the value of stress in concrete is going to remain constant, and that is going to be equal to 0.446 FCK. Therefore, in this assumption, we say that 3 by 7 xu is equal to df, which means on the entire df, the value of stress is going to be constant, and that value of stress is going to be 0.446 FCK. The moment I say 3 by 7 xu equal to df, we know the value of df, which is 90 mm. Therefore, xu turns out to be 7 by 3 times df. In this case, it is 210 mm. Now let us work out the compressive force at failure if 3 by 7 xu is equal to df. To work out that, we are going to divide this cross section into two zones. Zone number 1 is a rectangle we have to look at this stress block now. So zone number 1 is rectangle with size BW, that is 230, by XU, that is 210. Corresponding to this shaded rectangular portion on compression side, the value of Cu is going to be equal to 0.36 into FCK, that is 20, multiplied by B, that is 230, multiplied by XU, that is 210. In this, now we need to add the contribution of remaining portion. So width of remaining portion is going to be equal to BF minus BW, that is 700 minus 230. On this entire remaining portion, the value of stress is going to be constant, which is 0.446 FCK. Therefore, I write 0.446 into FCK into 700 minus 230 multiplied by depth of flange, that is 90 mm. Compressive force works out to be 725076 Newton, which is again less than TU. Therefore, 3 by 7 XU must be greater than DF. In other words, we must have more area on the compression side, and therefore XU must be greater than 210 mm. That means 3 by 7 XU must be greater than DF. Here, if this Cu would have been greater than Tu, then the conclusion would be 3 by 7 Xu is less than Df, but Xu is greater than Df. In that case, we would have calculated Yf as shown in the previous video. Yf is equal to 0.15 times Xu plus 0.65 times Df. And then we would have done the calculations in accordance with the steps shown in previous video. As this Cu is less than Tu, therefore we have a conclusion 3 by 7 Xu must be greater than Df. So now let us make that assumption 3 by 7 Xu is greater than Df. In that case, this stress block would look like, as you can see, 0.446 FCK is constant up to 3 by 7 XU, and this 3 by 7 XU is greater than DF. Therefore, on the entire flange, again, we are going to have constant value of stress 0.446 FCK. Now, let us write down the expression for Cu in terms of position of neutral axis XU. So that expression would be again written by dividing the cross section on compression side into two parts. One, this rectangle marked in orange color. So corresponding to this rectangular portion on compression side, the value of compressive force will be 0.36 into FCK, that is 20, into 230 into XU, which is unknown now. In this, we are now going to add contribution from the remaining portion of the flange. The area of remaining portion of the flange is BF minus BW, that is 700 minus 230 into 90. So this is the area of remaining portion of the flange on which there is the constant value of stress, which is equal to 0.446 FCK, that is 0.446 multiplied by 20. So if I add these two contributions, the total value of Cu should be equal to the value of Tu at equilibrium. Therefore, it must be equal to 886150 Newton. The only unknown in this expression is Xu. Xu works out to be 307.27 mm. Now let us calculate the neutral axis position for balance section. For balance section, the position of neutral axis from extreme compression fiber is given as KUB into 650. This turns out to be 312 mm because KUB for Fe415 is 0.48. So 0.48 into 650 turns out to be 312 mm. As the position of neutral axis is, as the value of XU is less than this value of XUB, therefore we conclude that the section is indeed under reinforced section, and therefore our assumption is valid. Now let us calculate moment of resistance of this under reinforced section. To write down this moment of resistance of this section, we will write down the moment of resistance corresponding to compressive force offered by this orange rectangular section. That will be equal to that compressive force multiplied by its lever arm. We know its lever arm is d minus 0.42 xu. So look at this expression. This is the lever arm, 650 minus 0.42 times 307.27, which is xu. And the compressive force offered by this rectangular section is 0.36 FCK BW into 307.27, which is xu. So this first term gives the contribution of this rectangular portion in producing moment of resistance. Now let us look at the contribution of this portion of the flange, which is shaded in red. It is going to derive its compressive force. The compressive force acting on this red shaded portion is going to be at the CG of this stress block, which is rectangular one, and it happens to be at the distance df by 2 from the top or from the extreme compression fiber. So it is at the distance of 45 mm from extreme compression fiber, and the tensile force corresponding to it, however, is going to be offered at the same location. Therefore the lever arm, this lever arm is going to be d minus this 45. So 650 minus 45. So this is the lever arm, 650 minus 90 by 2. And the compressive force acting on this portion shaded in red is going to be 0.446 into 20 into 700 minus 230 into 90. So if we add these two contributions in moment of resistance, then the total moment of resistance of the section works out to be 493.35 kilonewton meter. So now let us revise, let us summarize all these steps that we are going to use for analysis of a T section. First thing that we are going to do is we are going to assume that the section is under reinforced. Knowing the amount of AST and grade of steel, we are going to calculate the value of ultimate tensile force TU. Then we are going to make the first assumption that XU lies at DF. We are going to compute the value of CU. If this CU is less than TU, that means XU is greater than DF. If it is greater than TU, that means XU is within the flange or XU is less than DF. If XU is greater than DF, the next step that we are going to do is we are going to assume that 3 by 7 XU is equal to DF. From that, we will calculate the value of XU. Then we are again going to compute the value of CU. If this value of CU is greater than tensile force, then we conclude 3 by 7 XU is less than DF. In that case, we are going to calculate YF as shown in the previous short video, and then we are going to calculate moment of resistance following the steps shown in previous video. If the value of CU in the case where we assume 3 by 7 XU is equal to DF is less than TU, then that means 3 by 7 XU is greater than DF. In that case, we will compute the value of XU. We will show that this XU is less than XUB, and therefore the assumption of section being under reinforced is valid. And then we are going to calculate moment of resistance of a section as given in this expression. So let us stop for today. In next short video, I am going to summarize all the three cases that emerged during the analysis of T section. So let us stop for today. Thank you.